Hello. Good morning, good afternoon, good evening. Thank you for joining. My name is Ryan Siegler. I'm a data scientist here at KX. And today we have quite an exciting presentation for you. A little bit different than our normal live streams. Actually, today we're doing a joint live stream with Unstructured. And I'm joined here by Maria, who's a developer advocate from Unstructured. Maria, if you want to say hi real quick.
Hi, it's very nice to be here. I'm excited for this presentation, and I think we hope to see a lot of questions from you folks, and we hope to have some engaging discussions at the end of this webinar.
Perfect. Yeah, definitely looking forward to that. And right off the bat there, one couple housekeeping items. We have a comment section in the StreamYard app here, and we definitely encourage you to put your questions, put your comments in there. Our goal is to be interactive, like Maria said, and we hope to be able to answer all your questions. If there's some that we aren't able to get to, or maybe we don't know the answer to, we will get to you in the comments after the session. And secondly, I know the big question is this being recorded? And yes, absolutely, this session is being recorded. Right when the session concludes, it will be available on YouTube. So you can go ahead and rewatch your favorite parts or share it out with your colleagues or on LinkedIn. So yeah, questions in the comments, recording will be available. And I think with that's most of the housekeeping items. So Maria, if you want to take it away.
Yeah, absolutely. All right, I see that you have my slides already shared, so I'm just gonna jump straight into it. And I'm gonna talk about simplifying complex RAG with unstructured.io and KDB.AI. They're essentially, in my experience, two very complex problems when trying to build RAG applications, retrieval augmented generation applications. And these are preparing the data and evaluating RAG. And so in this talk, I'm going to try to show you how you can simplify the first of those problems. So preparing the data for RAG applications. And the reason it is complicated is because in most Gen AI applications and most RAG applications, you want to use unstructured data. Unstructured data in finance industry, in marketing, in manufacturing, in healthcare, contains a lot of valuable business-related, product-related, customer-related information that you want your chatbots to be able to answer questions about. And every industry generates a ton of PDFs, PowerPoints, HTML files, markdowns. According to some surveys and research, it's about 80% of all data generated by all businesses is contained in those types of documents. And these documents in their raw format are mostly unusable at scale for these types of applications. These documents also are contained in multiple different sources. So you may have an S3 bucket with your documents. You may have some important documents in Google Docs and in your Google Drive, or in Dropbox and Salesforce and SharePoint and Notion and Confluence. The list goes on. So first challenge is just to get those documents out of those sources before you can even process them and use it for your application. And then, of course, you're dealing with all kinds of different native file formats. Each of them requires its own approach for parsing the document, extracting content out of that document. So you may have rule-based parsers for something like a markdown file. But in certain cases, like PDFs and PowerPoints and images, rule-based parsers are just not enough anymore. And you may want to use an OCR model, a document understanding model, or maybe a VLM to get the content of the document to be able to use it in your RAG application. And of course, because these documents are unstructured, you also will see all kinds of document layouts, the tables, the images, text and columns in different reading order. You may have branding and visual elements here and there. Whether those elements are important to your application or not is another story, but there is no one single structure to these documents. And of course, on top of that, there can be all kinds of noise if we're dealing with documents that are scans. So how do we prepare all these documents for a RAG application? This is what we're going to talk about. Now, it is possible to build pipelines with, for a single type of document, and you may find some libraries for parsing Markdown or HTML. Beautiful Soup is a great library for parsing HTML. But then as you get more and more different types of documents, the complexity increases. You have to figure out how to connect to different data sources where the data originally resides, how to parse different types of documents, when to apply OCR, when to apply VLMs, how do you manage those prompts, how do you standardize the output across different file types, how do you scale your pipelines, how you maintain. So this gets very complex very quickly in a real use case. And we have seen a lot of messy, complicated pipelines that just take all the life out of people who have to maintain them. And so Unstructured is a startup that solves this problem and provides an easy way of preprocessing different kinds of unstructured data in unified matter, and so you can start building your RAG applications without having to worry about this step. And the way we do it is by offering 3 different tools. You have an open source library that you can just pip install in your environment and build your own preprocessing pipelines for 25 plus document types. We offer a serverless API, which can easily process batches of documents, and we can scale it for you. It is SOC 2 compliant, HIPAA compliant, and offers production ready functionality. Plus, it has several custom fine-tuned OCR models in there that are going to do a better job of extracting content from complex PDFs and PowerPoints and images. And then finally, I'm going to mention here the enterprise platform that we are about to release in a couple of weeks. This is something that's going to have even more functionality for enterprises. It's going to be a no-code solution for data transformation and enrichment with all the same functionality that serverless has, but also faster and with more different partitioning strategies in there. Now, I wanted to show you how this all works under the hood. And so for all of those products, this is what the transformation of unstructured documents looks like. You begin with your documents stored somewhere. They don't exist in vacuum. They already are in maybe in a S3 bucket, Google Cloud Storage, some SFTP folder, Confluence, Notion, and so on. Unstructured can connect to 20 plus different data sources. In the platform, I believe there will be about 50 different connectors, but on the open source side, and you can connect to 20 plus different sources. From those sources, we can ingest documents that are of 25 different file types. This includes PDFs, HTML, Word documents, emails, Slack messages, if you're connecting to Slack, Markdown, plain text, CSV, and all kinds of other documents. And then the documents go through partitioning step. Partitioning step returns standardized canonical JSON file for every type of document. And partitioning can happen via one of multiple different strategies. And we're going to talk about strategies on the next slide, actually. So we're going to shelve this for the moment. I'm going to get back to partitioning strategies in just a moment. Once you have the standardized canonical JSON that's going to be the same regardless of the document source or the document type, then you can chunk it, embed it, and load it into KDB.AI. Now, you can see that there's also an enrichment step here and also a VLM partitioning strategy. These are going to be available in platform only, so I'm not going to talk too much about enrichments in this particular talk, but it's just a little bit of a teaser. Now, what are these strategies? How do we go from a document, which is unstructured, to a standardized JSON? So if your document is a Word document, HTML, Markdown, or something like that, then you can use fast strategy, and this strategy is going to apply rule-based parsers to extract all the content of the document. And it's going to be incredibly fast and cheap. And if your documents are PDFs, for example, or images that are more complex and you cannot extract text from them with parsers, then you need to apply OCR and document understanding models. And this is when you will need to use high resolution strategy. And in certain cases, this is also not going to be enough. And so on the platform, we're going to feature VLM partitioning strategy that's going to use state-of-the-art VLMs to extract content from the most challenging documents where OCR is not enough. And finally, auto strategy, it's just a strategy that's going to decide which of the previous strategies to use based on the document type and complexity. But
hey, Maria, sorry to interrupt real
yeah.
quick. This is a quick question. I've been hearing an awful lot about VLMs lately, especially really like over the last 3 or 4 months, and how good they are, especially parsing things like PDFs. Do you see VLMs like really taking over OCR, or maybe like some sort of a hybrid approach potentially?
So it all depends on the use case ultimately. So for example, if you're working with very noisy documents with handwriting, VLMs are going to do a really good job. OCR can still do a great job with documents that contain printed text and tables and even with images. There is a hybrid approach when you can apply OCR to text, and when there are images and tables, you can apply VLMs to generate descriptions of those elements. And again, this is something that we're going to offer in the platform that is coming very, very soon. So I believe in about 2-3 weeks, it's going to be publicly available. I don't think VLM will fully replace OCR. There are certainly use cases where OCR is going to be faster and cheaper. VLMs are not cheap.
Yeah, true.
And so if it makes sense to use OCR, if OCR does a good job, I would say that this is the way to go. And VLMs, we tend to recommend them for the most complex documents where OCR struggles. But there's a place for everything. And in some cases, even for certain PDFs, you sometimes can use fast strategy that is designed for Word documents and Markdown. But if your PDF contains only text and no visual elements, then you can even go with fast. And this way you will get the cheapest PDF parsing out there. So it depends on the use case, as usual. There's no silver bullet for everything.
Yeah. Well, thank you.
Yeah, no problem. But moving on, I wanted to show you what the JSON output looks like. So I was saying that, you take different documents, different document types, and you get the same type of JSON as output. So here I have a page of a PDF document. This is an archive paper. And on the right, you can see 2 document elements from this document. I'm not showing the full JSON because obviously it's going to be super, super long, but I wanted to illustrate what the output looks like. And as you can see, we break down every document into these logical units. So you have the title, you have that element has the ID, it has the text, who validates the validators, and then there is some metadata that comes with that element. And then you have the next element, which is narrative text. It also has an ID. It has the text, this part about Shreya Shankar, the researcher, one of the authors of this paper, and so on. So the documents are split into these logical elements. So instead of giving you plain text of the document, you get this atomized little document elements with metadata and all the content and everything. These are the examples of element types that you can expect to see in this JSON document. So you have your titles, your addresses, tables, headers, footers, narrative text, list items, and so on. We also, so this way we preserve the structure of the document, but also the hierarchy of the document. So you have, for example, here abstract and then the paragraph. This part of the document, when converted to JSON, is going to be represented by two elements. The first element is going to be a title, abstract, and then it's going to have its element ID. But then in the narrative text element, you're going to see in the metadata the parent ID. So this is how we know that this paragraph belongs in this particular section. And this is helpful to know later on when we're going to be doing chunking. So I'm going to talk about this a little later. So to summarize this part, this is how we create this JSON document. We split the document into individual elements and preserve the logical structure of the document and the hierarchy of the document. But you also have seen in that example that we add metadata. Metadata comes really handy in a lot of RAG applications when you may want to pre-filter the documents using some metadata field. It also helps to curate data if you want to do so. So we try to extract as much metadata as possible from the documents. So this can be the language, the page number, when it was modified. If there are any links in the document, we're going to throw them in the metadata. If there are images, we can save them as base64 images in the metadata. If you have tables, we're going to save them as HTML, plain HTML tables in the metadata, and so on and so forth. As much additional information as we can get from the document, we're going to place all of that into the metadata. And so at the end, from 20 plus sources, for 25 plus different file types, you end up with a standardized JSON documents that have the text, the content of the document, the structure preserved, the hierarchy preserved, and all enriched with metadata. Now, I mentioned that the structure and hierarchy comes in handy when we chunk the documents. There's a lot of approaches to chunking, some simple ones like splitting based on the number of characters, some a little bit more advanced, using the information about the paragraphs and the sentences. Unstructured goes a little bit further, and we use several different strategies to ensure that when you chunk your documents, you do not mix information from different topics from different sections. So when we use, for example, the by title chunking strategy, we make sure that the generated chunks are not coming from different sections. So we use that document structure and hierarchy to track whether text belongs in one part of the document or the other, and we don't mix different topics. And we offer other smart chunking strategies that can take into account whether the text is on the same page, or even use a quick embedding to compare different elements to understand whether they cover the same topic or not, and whether they belong in the same chunk or not. And once everything is chunked, unstructured integrates with multiple different embedding model providers, such as OpenAI, Hugging Face, Bedrock, and many others. We do not host any of our own embedding models. We're not an embedding model provider, but we integrate with every popular embedding model provider. Actually, this list is missing Together AI, and it's missing Mixed-Bread AI. So there's actually more than more embedding providers supported. And finally, everything gets written into your favorite vector store. And I'm assuming since you're here, this is KDB.AI. And so I wanted to show what this pipeline could look like for processing the documents. And let's say we have the documents in an S3 bucket, and those documents are PDFs, and we want to automatically partition them into this JSON format. We want to chunk them, embed them, and load them into KDB.AI. And just to pause for a second, I want you to imagine that all the complexity that could go into that pipeline. And with unstructured, in this example, I'm going to be showing unstructured API and unstructured ingest library that helps to build these pipelines very easily. The pipeline is going to look like a small block of configuration files. And these configurations files are going to be the configuration for the whole process, like retries, number of processes, login verbosity, things like that. Configurations for the source of the documents. In this case, this is S3. So how do we ingest from the S3 bucket? What is the S3 bucket's name? Where should we download temporarily the result? How do we connect to that S3 bucket? A configuration for the partitioning step. So do we want to use high resolution strategy? Do we want to use fast strategy? Things like that. Chunker config, if we want to do chunking. So partitioner config is a mandatory. Chunking step and embedding step are optional. So, but if you want to do the full pipeline, then there is a chunking config, and you choose your strategy. You can set the maximum number of the maximum size of chunk and all the other additional parameters for chunking. Embedding, what embedding provider you would like to use, what model from that embedding provider you want to use to embed the chunks that you generated. And then we need 3 configs to upload the results to KDB.AI. So these define how we connect to KDB.AI, where do we upload those documents, and the stager just checks that everything is can be uploaded and there's no data issues with schema or anything like that. And that's it. So this is on a high level how easy it is to build data transformation pipelines with unstructured. Now, this doesn't have to be with S3. You can replace the S3 configs with configurations for Google Drive or Confluence, and the rest of the pipeline will be the same. It doesn't have to be with PDFs. It can be any other type of documents. But maybe if you are processing a whole lot of Word documents, then you will change the partitioning strategy to fast instead of high res. But this standardizes the whole process and makes it a lot more accessible, I would say. Now, let me show you a Jupyter notebook with an actual example of this pipeline. Let me just open Jupyter notebook. Meanwhile, if there are any questions, I'm happy to answer while I'm switching to Colab.
No questions in the chat yet, but definitely encourage anyone who has questions about unstructured or just the RAG pipeline. We know it can get pretty complex, so happy to field any questions on that as well.
Okay, I zoomed in. Is this large enough?
Yeah, I think that looks good.
Okay. Awesome. So let's look at this Google Colab and how you can build this pipeline. First, pip installs. In this example, I'm using unstructured ingest, as I mentioned before. And unstructured ingest is very modular, so you can specify which dependencies you're going to need for your pipeline. In this case, I'm ingesting documents from S3 bucket. They are going to be PDFs. I need a dependency for KDB.AI to upload the documents to KDB.AI, and I'm going to be embedding the documents with a model from Hugging Face. Now, and I'm also installing here KDB.AI client because I wanted to retrieve some results later on. Now I'm going to skip the imports. This is not the most exciting part. We need to set some environment variables. So we are going to need an API key for unstructured and API URL. You can get them on our website, and you get a 14-day trial that is capped at 1,000 pages per day. I'm obviously not showing my API keys here. For an S3 bucket, you need a set of standard variables, such as where is your bucket, what is its name, and your credentials to authenticate yourself to that bucket. We're going to be using this model from Hugging Face. I find that it is a very good baseline model for many use cases, but obviously you may want to choose a better embedding model depending on what data you're working with. And we're going to need to know the embedding dimensions of that model because that's going to affect the uploads side of the things. And to connect to KDB.AI, we need to have an API key and the endpoint. I'm sure Ryan is going to show you or tell you how to get that information if you're getting started, or maybe we'll share some links later on. So I first need to create a table in KDB.AI before I can upload anything into it. And to create a table, I need to set up a schema here. I'm going with the most basic schema. My documents are going to contain element ID, the document itself, the metadata, and embeddings. And we're going to use the HNSW index. And here's where the number of dimensions is going to come in handy, because we need to know what size of the vectors we are producing, what size of the vectors are we going to be storing here. Okay, I'm going to make it a little smaller because this code does not fit into the screen. I think this way it fits better. Yes. Once we create the unstructured demo table, we can create the pipeline to process the documents and load them into KDB.AI. And this is what the pipeline is going to look like. Just as before, it's going to be a pipeline that we're going to build from different configurations. So think of it as building with Lego bricks. You have to build this pipeline and you just plug different things and connect different things together. I'm going to use the most basic processor config with the defaults are going to work just fine here. I'm going to connect to the S3 bucket that I defined in those environment variables earlier. And I'm going to be sharing this notebook later on, and you're going to get a link. So if you don't want to play with an S3 bucket, and if you want to try it out with just local files in this in the folder, then you can just comment out these three configurations and uncomment these three. And this way you can just replace the whole pipeline from an S3 bucket from using S3 bucket to using a local directory with files. partitioner config. Because we're partitioning by the API, this flag needs to be true. And then we just need to specify the credentials that we use to connect to the API. And because these are PDFs, I'm going to be using high-res strategy because they're images and they're tables, and they're not, this is not a simple PDF that could be processed with fast strategy. For chunking, we're going to go with the smart strategy called by title, which is going to preserve the structure, which is going to take into account the structure of the document and make sure that chunks do not contain information from different sections. This is helpful to improve the retrieval results when you don't retrieve information from different topics. For the embedding model, as I mentioned, I'm using the embedding BGE base model from Hugging Face, and I just need to tell unstructured ingest which provider to use and which model to use. And finally, destination connection is configured in just a few lines of code. So you need to provide your credentials and an endpoint and specify which table you want to upload the results. And just like that, in, I don't know however many, but I think it's about 20 lines of code, maybe a little, no, it's a bit more, but depends how you format it. It could be 20. That's all it takes to process all those documents. Once documents are in that table, this is what they're going to look like. Oops, scrolled back too far. And this is it. Now, we split this webinar into two parts, and Ryan is going to show you how you can build an actual RAG application using the data that has been pre-processed with unstructured. And for my part, I just wanted to show how quickly and easily you can pre-process different types of unstructured data from multiple different sources, all streamlined into your KDB.AI table.
Great, thank you, Maria. And we just had a couple of basic questions here. Can we get a copy of the notebook? And yep, we will definitely be sharing the link to the Colab notebook to you all after the session. And yes, this is being recorded, so it will be available on YouTube right when the session ends. So yeah, any other questions about unstructured, put them in the chat, and then at the end we'll field all those. So thank you so much, Maria, for your part of the presentation. And then I'll just switch it over to my slides right here. Okay, I think we're good. So Maria talked about, the first and really a very important step of the RAG pipeline. That's, of course, getting your data ingested into the vector database. And there's so much that goes on in that process. And yeah, like you said, you could do it manually, but unstructured gives you a much better way to do it. And you get to do it in one swift step, like she just showed you. 20 some lines of code, and that entire pre-processing pipeline, from ingestion to chunking and embedding, that's all taken care of for you. So it's a really good way to go about this. And now I'm gonna take on sort of the rest of the RAG pipeline, and with a focus on the vector database, KDB.AI. So just a quick little intro on KDB.AI. There's a really nice free trial we have available. If you go to KDB.AI, there's this little sign up free button here. If you click that, you'll come to another screen where you can just throw in your email, and you can get signed up for a free trial of the vector database. Once you're in there, we have a nice cloud UX environment here where you can see an overview of the tables that you have and whatnot. But really, the most important tab here is once you create your account, come over into connection details. And here is where you can find that endpoint and the API key. You can add your API key. And this is really important because once you have these two things, really the world's your oyster as far as vector databases go. So get your endpoint, get your API key, and then you can come on over to the sample applications tab. And we have several different sample applications, including some RAG pipelines that you can get started with, open it right up in Colab. All you'll have to do is put in your API key and endpoint that you have right here, and you'll be able to get started with a RAG pipeline from not even having a KDB.AI account to finishing your RAG pipeline you should be able to do that entire process within like 5 to 10 minutes at the most. So easy to get started. Definitely recommend checking it out. And then, one of the things that we focus on at KX is really trying to create a good developer experience. And that starts with the free trial that we have. And really, in my opinion, at least, I think it's one of the best in class free trials for vector databases. We have both cloud and server version available as a part of that free trial. So whatever one you're interested in, easy, have it hosted on the cloud. I like working with that one, but if you wanted to host it on your own infrastructure, you have that option as well with the server version. The nice thing about working with the cloud version is we're not going to delete your data unless you're inactive for 30 days. So you can create, as many tables and databases and indexes as you want on the cloud version. And as long as you're active in a 30-day span, that data is going to stay there. One of the powerful parts of KDB.AI is you do have the ability, even in the free trial, to create multiple databases. Within each of these databases, you can create multiple tables, or like the vector databases, vector indexes, and then within each of those tables, you can actually have multiple indexes. So that's really good for things like multimodal RAG or hybrid search, things like that. One of the other things that we put a lot of focus in is extensive developer resources. So we have several different developer resources. We try to make it really easy to learn all this and just to become more knowledgeable about generative AI as a whole too. So we have something called the KX Academy. It's a free resource. You can go on there and take courses on all sorts of different topics, including vector databases. So one of our other developer advocates, Michael Ryboy, created a really nice vector database course, taking you just from the basics of vector databases all the way to really some pretty advanced search methods. So definitely recommend checking that out on the KX Academy. And then I think the biggest thing I want to highlight here is our Slack channel, because this is where you can get direct access to myself and the other developer advocates on the team. Ask your questions, stay updated. It's a good active community. So definitely join that Slack community, and I think you'll get something out of that. We have Learning Hub that has all sorts of articles, GitHub that has like a ton of different samples, including several RAG pipeline samples on there. So if you want to dive into the code a little bit more, GitHub's your place. And then of course, YouTube. This is all going to be recorded. It's on our YouTube. And if you want to watch previous sessions, all that's on our YouTube as well. So just a little rundown of the resources that we have for you. Awesome. So let's get into the fun stuff now, talking a bit more about vector databases and KDB.AI. So really the whole point, in a sense, of a vector database is to do really effective, efficient, and scalable similarity search upon your data. And I like this little architectural flow here because it shows you really how simple it is in a sense, but each of these steps on its own, it can be quite complex. So you start with your source data, it could be documents, it could be images or video, audio even, and then you take that data and you run that through an embedding model, which is just a deep learning model that sort of transcribes your raw data into numerical, machine readable vector embeddings that hold the semantic meaning of the original data. Well, the beautiful thing about unstructured is unstructured takes care of all this for you. So once you set up that unstructured pipeline, this becomes that one swift step. And then we have that integration now. So KDB.AI now integrates with that unstructured framework, and we can get this source data embedded and inserted into KDB.AI really quickly. And then once you have your data in KDB.AI in that vectorized format, the power of it is you can send in a query or a prompt, for example, into your vector database, and the vector database does this similarity search that says, hey, what are the most semantically similar documents to that user's query? And say you want to return the top 5, for example, most similar documents. You return that as your output, as your query results, and then you can pass that down to the rest of your whatever application you want, including a RAG pipeline, for example. So of course, RAG is like all the rage now, but there's plenty of other use cases that you can use vector search for, including just like basic document search, things like sentiment analysis and pattern matching recommendation systems. Image similarity search is sort of an interesting one. We have a really good demo on our GitHub that dives into image similarity search. And then, of course, all the RAG use cases. You talk about multimodal RAG, multi-index search, hybrid search, and then temporal similarity search. I'm going to touch on this just a little bit later quickly, but this is using time series data in your vector database. So pretty interesting use cases there. Okay, so let's talk a bit more specifically about RAG and how this works. So RAG really just empowers users to ask questions to a large language model, because we know large language models, they're amazing. They can answer all these questions, but they don't know about your own personal data. They don't necessarily know about your enterprise data because they weren't trained on that. So RAG enables us to present that data that an LLM has never been exposed to the LLM in a really efficient way and a very precise way, so that the LLM can then answer questions about that data. So for example, like enterprise data, or say there's some newly released technical articles or documentation that the LLMs haven't been trained on yet. Well, you could use a RAG pipeline to present specific pieces of that information to your large language model. And really there's two key steps to how this works: retrieval and generation. Retrieval is where you extract that relevant data using a vector database and semantic similarity search from the vector database. And then once you retrieve those relevant pieces of data, you then present those to a large language model, where it can then generate a response. So retrieval, get the most relevant stuff from the vector database; generation, feed it to an LLM and get your response. And these are the two like high level steps. And there's smaller steps within this, but that's really the core of how RAG works. Okay, so a nice little architecture diagram. I like these. I think it's a really good way to sort of visualize how this works. And you have your data. We're going to use documents in this example. And we have unstructured here that takes care of this entire ingestion, chunking, and embedding step for you. So your data really gets shipped in through unstructured, ingested, chunked, embedded, and then we have the integration now with KDB.AI. So now we have all of our data as vectors in our vector database. And this sets us up for that first step of RAG, which is the retrieval step. So we have our user. They want to ask a question about some of this data, and that user prompt is then embedded in the same way that our data was embedded, typically using the same embedding model. And then because they use the same embedding model, technically our user prompt embedding and all of our vectors in our vector database are within the same vector space. So that means we can do a semantic similarity search between them. Things like Euclidean distance, cosine similarity, dot product, just some different methods of how you can do that search. But you're just comparing this vector to all the vectors in your vector database to find your top n or top k most similar vectors. And that's your retrieval step. So you do your similarity search and you retrieve the most relevant data here out of your vector database. And then for generation, you just pass this data alongside your user prompt to your large language model, where it can then generate you a response. So that is the basics of your RAG pipeline. Okay, so there's some ways that we can optimize this, and this isn't necessarily a deep dive into optimization today, but I want to highlight a few of the things that are unique to KDB.AI that can specifically help you with your RAG pipeline and just with retrieval in general. So one of the first things is on-disk vector indexing. So we have all the key vector indexes like flat, HNSW, IVF, PQ, all these different indexes that are available. But the thing is, these indexes are typically held in memory. So that means all your vectors are in memory. And unfortunately, as we know, memory can be very expensive, especially working at scale. If you're talking about tens or hundreds of millions or maybe even into the billions of vectors, storing all these vectors on memory is going to be very expensive, and that's probably going to cause some problems. So we have a couple proprietary indexes that are on disk, and we have something called QFlat, which is just a flat index that's on disk, as well as QHNSW, which is a HNSW index that's on disk. So a couple of the really nice things about this is if you are inserting your data, or as you are inserting your data into KDB.AI onto one of these on-disk indexes, it's going to be very low memory on insert. And then on your actual search, it's going to also be very low memory. So you're storing all your vectors on search. These vectors are on disk, and then these vectors are memory mapped into memory. So really what you're getting is like the best of both worlds. And it's going to be a much more cost-effective solution at scale than holding everything in memory for the entire time. And the nice thing about on disk too is that your index can grow and it's not really limited by memory constraints. So like a situation where you might be constrained on memory, say you're working on an edge device. In this case, memory may be limited, so using an on disk index may present a better option. And then some of the other things that you could do to help increase the efficiency of your RAG pipeline and retrieval are metadata filtering. I know Maria briefly mentioned this. Metadata filtering is actually built right into KDB.AI. So this is great because you have unstructured, which just took all your data and extracted it and loaded it into KDB.AI with metadata fields as well. So you can use those metadata fields and apply filtering to them. And I'll show a little bit of that just in a moment here. But the beauty of metadata filtering is it shrinks your search space because you're applying a filter to all the vectors in your vector database before you're even doing your similarity search. So because you're now searching over less vectors or fewer vectors, you're going to increase the accuracy of your search and you're going to increase the speed of your search. And then one of the really awesome things that we just added recently is called fuzzy filtering. So it's like an extension of metadata filtering, but fuzzy filtering. So if you had some typos, for example, in your metadata fields, or some international spelling variations, our fuzzy filtering is going to be able to handle that no problem. And I know I've actually seen this in some past work that I've done where you may have a massive database, for example, that holds information about different manufacturing machines, where they all have long numeric and string IDs, and some of those were entered by hand and there's some typos in them. Well, with fuzzy filtering, that's going to solve that problem for you. So just another feature to help you out in your retrieval journey. And then the last slide I'll do before we jump right into the code is just a quick touch on temporal similarity search. So this is one of the really unique features with KDB.AI, and it allows us to do similarity searches, pattern matching, and trend understanding, as well as outlier detection and anomaly detection upon time series data. So there's a couple different methods we have. I won't get too deep into it, but basically you're able to do temporal similarity searches, we call it, whether you're looking at like a really massive historical data set or like a reference data set, or even like on live streaming, fast moving time series data. So whatever type of data you have, you can actually use KDB.AI to do this type of pattern matching on it. And if you're interested in that, we just did a live session a couple weeks ago that dives into this with a really cool stock market analysis demo. So check that out on our YouTube. Okay, I think that covers my slides. And let's go ahead and jump right into the code now. All right. So I had, my runtime disconnected. All right, perfect. I'm going to rerun some of these cells, but it shouldn't take too long, hopefully. So what we're going to do here is sort of take what Maria has done and loaded all that data into the KDB.AI vector database, and now we're going to take that and complete the RAG pipeline. So we'll do our imports, and what we need to do is just put in our information for our KDB.AI endpoint and API key. And like I said, you can easily get this by signing up for free for the KDB.AI trial. And it's as simple as just putting these endpoint and API key in, and there you go. We're able to be connected to KDB.AI. We just connected to the session there. And then because I already created the table that Maria had created, we're just going to load that table into this instance. So we just go ahead and grab that table I created. And I did one minor modification to the table. I actually used the Q, H, and SW index just to highlight that we have that on-disk index available to us. And it has all the same capabilities as a typical in-memory index. So all we're doing is just connecting to that table. And we can take a look what's inside. And we can see all the different things that we have inside, all these different document chunks that we have here. So all those columns that Maria showed earlier are within this KDB.AI table. And also, if you want to take a little closer look at the metadata, I just took the first row of metadata just so you could see the type of metadata that is extracted using unstructured. Okay, so now what we're going to do is actually set up our RAG pipeline, and we're going to do this with the sentence transformer model, the same one that was used with unstructured, because we're going to use this to actually embed our user's query. So we use that same embedding model. And then what we're going to do is set up this RAG pipeline. So the first thing that we need to do here is embed that query. So we create a query or a function that embeds this query. And then we need to go ahead and run a search, and this is that retrieval step. So we embed the query, and then we're going to run our search on that query. So all we're saying here is our table that we just grabbed before, dot search, and then we say vectors is equal to QH and SW. So that's our index that's within our table. It's a QH and SW index. And then we were just sending in that embedded query and then returning the top 5 results. So in this line of code, we're actually going out and doing retrieval. So that's just our function to do that. And now let's actually try it out. So let's do some retrieval. And the document that we're working with is I believe a 10K document. So it's a financial document, and it has all sorts of information like about the previous year and the financial results and different information about the company. And one of the things they talk about in there are how many employees they have. So let's just see, can we retrieve some of those chunks that talk about the employees. So if we do this, we're actually running that retrieval step that we just defined above, and we get our top 5 responses. And if you read into each of these pieces of text, you'll see they are talking about the number of employees that the company has. Now, like I mentioned, we'll do a little dive into metadata filtering. And really all we're doing here is the same exact thing that we were before, but we're adding this filtering step in. And all we're doing here is adding this filter in that says like within that document column and employee. So what I'm saying here is I simply want to find and retrieve documents that have this string in it, the employee string. So this is a version of how we could do metadata filtering to help narrow our search results. So we'll define that function and then run the same query with that filtering function. And if we look in here, every single document would have the string employee in it. Okay, so the last thing we'll do is just a quick example of fuzzy filtering for the retrieval step. So with fuzzy filtering, what we're doing is we're going to take an example with the ID column. So if we look above, we have our ID. It's just a bunch of basically just a bunch of string IDs here. And I know for a fact that we have an ID in here that looks like this. So 95DC right here. So this is the first one. But what I want to do is I want to test fuzzy filtering here. So what I'm going to do is I'm going to take this D and change it to an E, like there was an accidental typo with this ID, for example. And then what this is going to do, ideally, if this works, which it should, is it will still return that as a result because we're filtering it. And even though there's a typo in there, it's still able to go ahead and grab this this retrieved chunk. So that's a really powerful feature. And this is just sort of a silly example just to show how fuzzy filtering works. But in certain use cases, you're going to have dozens of metadata columns where you may actually have typos or those international spelling variations, and you still want to do metadata filtering. Using fuzzy filtering is going to be a perfect way to help you out there. Okay, so let's get to the final step, which is generation. And here we're going to go ahead and put our API key in, which I already have here, perfect. And we're going to use OpenAI. And what we're going to do, and a lot of times with RAG pipelines, you might use LangChain or you might use Llama Index, and that's great. I use those all the time, but sometimes I like to just do it manually and just see how this works behind the scenes. All we're going to do is pass in our retrieved results, which are those 5 results we had above, as well as our user's query. We're going to append all of those 5 results together into one big string, and then we're going to pass that into the system prompt here. So we're going to pass those extracted results as well as the query into a prompt, and then pass that into our OpenAI chat completions function right here. So this is what is actually going to go ahead and call the OpenAI API key. And in other words, this is your generation step of the RAG pipeline. So we'll define these functions, and then let's go ahead. We'll see if we can get this to work. We have the correct answer is 316,000. So if we do this, hopefully we'll get that. There we go. Perfect. So it was able to correctly identify the number of employees that the company has. Okay, so that covers my demo. Did we have any questions in the chat? Let's take a look.
Yeah, there is a couple of questions about unstructured. I'm happy to answer.
Perfect.
So one was from Jacob. Is there an easy way to extract specific elements after processing with unstructured to create tabular data from unstructured data? Can we use the JSON format you showed to extract customer ID, deal numbers? So in my example, I showed how you can upload the data into KDB.AI, but you can also, for example, upload those JSON documents into a local directory, and then you can mess with those documents however you want. You can just extract data from those documents, like specific customer IDs, deal numbers. You can modify and do whatever you want with those documents. I have a notebook that I can share in which I show how you can process that data, save JSONs locally, extract custom metadata specific to a use case, add it back to the JSON, and then upload it into your destination. So that is also possible. The reason why we do not extract specific kinds of information like that by default is because it's very use case specific. You know your data, you know what kinds of additional metadata fields might be useful to you. And in the platform that we are about to release, there will be an option to add custom metadata enrichment step, so you can define what exact maybe named entities you want to extract and add as metadata, maybe document summary as metadata, maybe customer ID, maybe a metadata from somewhere else. So this will be possible to do in platform, but there is a way to do this with ingest right now as well, and I can share a notebook that shows how to do that. And there was another question about document processing by Panuka. When a document is ingested with chunks associating parent ID as per the document structure, at the retrieval step in RAG, just the heading may come with the higher ranking in the answer if the user question query is on a particular title, but the actual content may not come at all if there's no matching words. How to overcome this challenge by dealing with the parent ID associations. So it depends how you set up your retrieval, really, because you can choose to retrieve everything from the same section, because that information is stored in metadata. You can use that information to make some really complex things like graph RAG, for example, if you want to. But with chunks, one of the things that unstructured can do is when chunking the document, it can not only split large chunks into smaller chunks, but it can also merge small chunks into a larger chunk, which can help in this situation. So then the heading will get merged with the first part of the section. So you will not get just the heading, you will get more than that. It may not necessarily be the whole section, depending on how large the section is. It may not fit in the whole chunk. So you may still want to retrieve all the other parts of that section, but that's that may be enough, depending how your document is structured, depending how big the sections are, depending where the information is contained. This is one of those situations where you really need to look at your data and figure out whether just merging chunks will be enough, or you need to do something more complex, like retrieve everything from that section, or do even more complicated things like graph RAG. So I hope that answers your question. And speaking of more complex ways of doing RAG, Ryan, you mentioned different indices and different retrieval methods. And I was wondering if there are other ways to optimize the RAG pipeline that you can do with KDB.AI.
Yeah. So yeah, I mean, there's multiple ways. Obviously, like metadata filtering, I just went over is a really good way. But one of the really cool things that we're looking at right now is integrating and using re-ranking in your RAG pipeline. And that's a really powerful method, because what you have with retrieval is like a really fast vector search that's extremely scalable. So millions of documents really. And then once you get your top K documents out, they're going to be relevant to your query, but they may not be like the top number 1 or 2 or 3 may not be the absolute most relevant. So what you can do to make sure that the top chunks that you're returning are absolutely most relevant is put a re-ranker as well onto the end of your RAG pipeline. And all that does is do basically a large language model style re-ranking between your query and all the retrieve chunks. So it's kind of like a second stage to retrieval in a sense, where you're able to get even a more accurate retrieval out after you do your main vector retrieval across the massive data set. Now, you might ask, why wouldn't I just do re-ranking on all my documents? Well, the simple answer is because it's expensive and it would take too long. So you take advantage of the vector database to do that initial search, and then re-rank on the smaller subset to get the absolute most relevant documents that you can then send to your large language model. So that's one of them. And then I think one of the big ones too that we're really excited about is the on-disk vector indexing. Like I mentioned, you're in a memory constrained environment, especially IoT, for example, where you are running on smaller edge devices. Memory is at a premium. So being able to store vectors on disk in that instance could be really helpful. Or if you're working with like billions of vectors, storing all those vectors in memory is just going to cost a ton of money. So why not use disk? It's way cheaper. So that's one thing that we're super excited about as well. All right. Well, I see if there's any other questions that came in here. Are there forums that we can discuss these strategies on? And at least from our side, yeah, absolutely. So we have a Slack channel, kx.com/Slack. Join it. We love having discussions on there. If you have questions about the product, ask us. You get a direct line to myself and the other developer advocates on the team. And it's a really good active community. So definitely check that out. And I don't know, Maria, if you guys had something from your side that you'd like to have discussions on and whatnot.
Yeah, absolutely. I was just I was copying the link to Slack, and I just shared it in the comments. So this is the unstructured Slack that has a community, and you can join it to ask your questions, to chat with our engineers and developer advocates and support folks. Yeah, everybody's welcome.
Awesome. And then there was one other question. It looks like, I think this is probably for unstructured. Does the pipeline include anonymization capabilities?
No, it does not, because again, this is very use case specific, whether you want to remove some information or not. I have shared a notebook in the comments where I show how to do a PII removal while using ingest, and in the platform that is going to be one of the, again, custom enrichment steps if you want to do that. So we tend to extract as much as we can, and then whatever is use case specific and requires the decision makers to understand the data, to understand the use case, these steps should be customizable. We should not be opinionated on what you have to leave in those documents, what you should remove. You should be the ones deciding what is important for your use case to keep in your data and what you may want to either throw away or change in one way or the other. This is very use case specific.
All right, thank you very much. And I think that concludes all the questions that we have in chat. So yeah, I think we can conclude the session. Just want to say, a big thank you to you, Maria, and Unstructured for joining. Really enjoyed your presentation. It's awesome to see, even with the complexities of data ingestion, you can make it much easier using Unstructured. So great demo. And thank you all for joining. We really appreciate your time coming out to learn a little bit more about Gen AI and RAG and all this fun stuff. So thank you for joining. If you have any questions, reach out, connect with us on LinkedIn. We're happy to have these conversations. And just a heads up, so on December 4th, we do have another session. We will be talking about historical and real-time analytics within Python. So really excited about that session. So if you're interested, you will be seeing a sign up on LinkedIn for that very soon. And I think that covers everything. So again, thanks everyone for joining and have a great day.
Thank you so much. Hope you enjoyed it.